Quantum location, a study in probability and measurement. In classical physics, location is a simple matter. A particle or an object has a definite position at all times. You may not know exactly where it is, but Newton would insist that it exists at a fixed point in space, regardless of whether anyone is observing it. Quantum mechanics, however, undermines that certainty. In the quantum world, location becomes a more subtle and elusive concept, described not by a fixed coordinate but by a mathematical object known as the wave function. The wave function and probability. The wave function, symbolized by x, is the foundation of quantum mechanics. It does not tell us exactly where a particle is. Instead, it encodes the probability distribution of finding the particle at a particular location when measured. The square of its magnitude, (2), gives the probability density for position. This means that before observation, a particle is best described as a spread-out cloud of probabilities, not a point with definite coordinates. This view does not imply that a particle is literally smeared across space, existing in all those positions simultaneously. Rather, it reflects our fundamental limits of knowledge. Until a measurement is made, location is not an intrinsic property but a spectrum of possibilities, measurement and collapse. When a position measurement is performed, the wave function undergoes what physicists call collapse. The diffuse cloud of probabilities sharpens into a single outcome. The particle is found at one location. After this collapse, the particle behaves, at least momentarily, as though it has a definite position in the classical sense. Yet prior to measurement, no such definiteness exists. The idea that the particle has been sitting quietly at that location all along is a tempting but inaccurate classical intuition. Uncertainty and the trade-off with momentum. Location becomes even more tangled with momentum due to Heisenberg's uncertainty principle. The more precisely one measures a particle's position, the less precisely one can know its momentum, and vice versa. This principle is not a technological shortcoming, but a fundamental feature of reality. A particle cannot be nailed down with perfect certainty in both space and motion, which places intrinsic limits on what location can mean in quantum theory. Entanglement and position entanglement complicates the picture further. If two particles are entangled in position, then measuring the location of one provides correlated information about the other. Yet even in such cases, neither particle possesses a definite position until measured. Entanglement creates astonishing correlations across distance, but it does not provide a cosmic tracking device. Location is still locked behind the probabilistic veil of the wave function. From the quantum to the everyday, one might wonder why macroscopic objects, such as coffee cups or cars, do not blur into probability clouds. The answer lies in decoherence. Large systems constantly interact with their environment, forcing wave functions to collapse so rapidly that superpositions are effectively destroyed. The quantum fuzziness still exists, but on such tiny scales that it has no practical impact. Thus, the familiar solidity of the classical world emerges from the quantum one. Conclusion. In quantum mechanics, location is not a fixed, ever-present fact. It is a probabilistic property encoded in the wave function, revealed only through measurement, and subject to fundamental limits imposed by uncertainty. Entanglement can link particles across vast distances, but it does not provide positional knowledge beyond the probabilistic framework. Unlike classical physics, where here and there are straightforward, quantum physics offers only a shifting landscape of probabilities until observation pins down a single reality.